All right, recording is rolling. It is Friday, January 26th. I know today's club photo day. Let's do a quick look at the clubs for this class period. I know you guys got pictures, then go ahead to the gym when you guys got to go. All right, so we got dance team going on right now. Then we got troop 7083, so that's a theater, right? Do that picture. Odyssey of the Minds, Key Club, Dungeons and Dragons, Mock Trial, book club, right? And okay, right, and those are all the ones during this class period. So right, if you're in any of those, then go when you got to go. Right. So our main thing today is going to be ray diagrams with refraction. You guys remember a few days back we did reflection, right? So we're looking at reflective surfaces, mirrored surfaces, right? Things like maybe these parabolic mirrors, for example, right? We did those ray diagrams the other day. Okay. Today we're going to do ray diagrams for refractive lenses. So I'm thinking like, right, so like refraction, say like this magnifying glass right here, got, right, or if you're wearing eyeglasses, right, looking at refractive lenses, something like that. Right. Think, okay. And then, speaking of eyeglasses, I always have to look this up, but I found in Paul Hewitt's book here, what kind of eyeglasses do you have for farsighted or nearsighted? So let's do that fast. Okay. So farsighted, and I Googled this. Let me get this right in front of me. Right. What percentage of people are farsighted? Right. So Google's top hit says somewhere between 5 and 10% of Americans anyway. So 5 or 10%. This is the less common one. Right? Means that your eyeball is squished like this, which means that the lens inside your own eye is focusing the light behind your retina. So you need a corrective lens to, well, make it focus on your retina, right? Right, and that's going to be a converging lens. And a converging lens, this magnifying glass is a type of converging lens, right? Where it'd be thick in the middle and then thin towards the rims, right? Now, if you're nearsighted, okay, that means your eyeball is elongated, so the lens in your eye is naturally focusing the light before it even hits your retina, right? So to correct that, you need a diverging lens, and that'd be one that's thick near the rims and thin near the center. Right? That's the kind I have here. Right? That's a lot more common. So according to Google, that is 41.6% of Americans. Right? Oh, so they have a real precise one on the number for that one. Right? So there you go. So about 5 or 10% here, about 40% here. Right, there you go. Right. So there's eyeglasses. Right. And we're going to be doing the ray diagrams today for the basic physics behind optometry. We got rocket launches coming up. Yeah, so we're always, I always appreciate that we're in Brevard. We can see these rocket launches. We got one on Sunday. There's this like 4-hour window. It starts about 6 p.m. Right? And there's one on Monday around noon. So there you go. Right. Also, we're going to have a little bit of extra time. So let's do a quick fun activity here. And switch my screen over. Okay. Let's do retinal fatigue. I know I did retinal fatigue the other day. Here, go ahead and stare at the dot right in the center. You guys are staring at the dot in the center. Okay. I know I did one the other day. Some students said it worked, some didn't. But in the past, I've always done it on my screen, and it's always worked. So if it didn't work the other day, maybe this one will work. Okay. Also, this was real basic colors, right? 4 colors. Okay. So remember what's going on here is you have 3 different color detection cones in your eyes, right? Red, green, and blue, right? RGB, right? So maybe like the bottom left is like wearing out your green cone. I mean, this is just temporary, right? It only lasts like a few seconds, right? Right. So I'm about to flip the screen to a white background, and since your eyes will have adjusted to the environment that you're getting used to right now, right? You'll see the flipped color, the inverted color, right? Right, guys, ready? Right, and pow. All right, you guys see opposite colors, maybe? All right. All right, so it only lasts like 10 seconds, and then your eyes get back to normal. All right. All right. I've got a whole folder of these. Let me flip to, let's flip through these. All right, so some of these work better than others. Right, now that one, if you have just a regular flat flag, it works pretty good. But this one is kind of a photograph, so photographs are tricky. There's so many slightly different colored pixels. It's like, I mean, so that one kind of half works. Right, that one's kind of tricky. It sort of works. Right, I think that one's pretty good. Right, let's do this one though. Let's do this one. Right. Yeah. So they're about as tag for some time. Hey guys, more or less adjusted from the previous one we did. If you want to make one of these yourselves, remember, if you can find something with just a basic number of colors, something cartoony, right? It works better than a photograph, right? You can take that picture, post it into Paint. I think it's a Control-Shift-I will automatically invert all the colors. So you can make your own if you like that. All right, let's flip this guy. Pow, Scooby-Doo. That won't work. Maybe say like a big brown, Great Dane. All right. Maybe. Yeah, it's a little bit more complicated than 4 colors. All right, so back over here. All right, let's do some ray diagrams for refraction. Right? So think about refractive lenses. Right, so you guys got paper. Does anybody not have paper? You guys all got paper, right? Right. Ooh. Let's see. Yeah. Tucker wore a good shirt today for this one. Oh, yeah. Think about physics today. Probably so. Yeah, that's what it was. It's like, wear that shirt. Good. Refractive lenses. So put your name on your paper. Name. Right. And let's call this ray diagrams dash refraction. Okay. So we're going to do refractive lenses here. Right. So we're going to do 6 examples. 3 on the front, 3 on the back. That's kind of like format we did a few days back. Right. So I'm going to dash off 3 horizontal lines on the front, and later on I'll do the same thing on the back. Right. So about the middle of the paper, about a quarter of the way up, and about a quarter of the way down. Right. There's like so 3 different baselines. Okay. All right. So let's do converging lenses. We'll do 3 converging lenses here, and then on the backside we'll do some diverging lenses. Right. So converging lenses. Right. Remember, this could be a magnifying glass. This could also be, if you're farsighted, which is less likely, but it's about 5 or 10%. Right. Maybe have eyeglasses that are similar to what we're doing right here. So let's get some converging lenses. Right. So think about refraction, refractive lenses. Okay. So here. Of course, if you have an eyeglass prescription that's unique to you, and there's like a very special way that your eyeglasses are curved, right? You're just doing the very basic physics principles, right? Okay. So I remember for reflective mirrors that we did the other day, they're like a bajillion different rays of light bouncing off those in all different directions, but we could just follow like 2 rays of light and figure out where was the image going to be. Right? And similar thing here, right, is we just follow like a couple of rays of light and figure out where the image is going to be. Okay? Well, I need to somehow define how tightly curved these are, and I'll do that with focal points. Okay? You guys remember focal point? Now, for the reflective mirrors, there was only one reflective side we cared about. Right? It made it either concave or convex. Okay? But for these refractive lenses, well, isn't it true that, here, got one right here. Let's try this. That if I hold it this way or if I flip it upside down, it's the same both ways, right? Right. So it's like symmetrical, like 2-way, refraction, but light's going all the way through. So I'm going to represent that by drawing a couple of focal points. Focal point there, right? Because you could play this either way. Right? And let's go on down the page. I'll just have these focal points spread progressively further out. So focal point there, and I'm using my ruler to make sure they're equidistant. I got like 2.5 centimeters, 5 centimeters, 5 centimeters. If yours aren't exactly those numbers, it's okay. I'm gonna do 10 centimeters away and 10 centimeters away from the center. Right. Focal point, focal point, focal point, focal point, something like that. Right. Okay. Now, how could you interpret what we have established so far? Right. We might call this really tightly curved converging lens at the top, and then maybe flatter as we go down. Right. Or another story you could attach to this is if you draw in an object. It's like say put an object right here, object here. Or how about object? I want to do this. About like right here, object. Right. You could think about where's the object relative to the focal point, kind of like the first one he's outside the focal distance, and then second one he's on the focal point, and then the third one he's just inside the focal distance, right? So like where's your object compared to the curvature of the refractive lens, right? Right. Let's do the actual science with this first, and then we'll do the ray diagrams and see if it actually aligns with the story, right? Like this, I got one of these right here, this magnifying glass, right? Or it could be a magnifying glass, right? If I hold it kind of close, see, it doesn't magnify a lot. Pull it back, ooh, it looks like it's magnifying a good amount, right? So what I'm thinking is maybe this last picture, when we eventually get to this one, I bet this last one is a magnifying glass where like the object is inside the focal length, focal distance of that that refractive lens, right? I bet this last one's going to be a magnifying glass, right? But what about how could I sort of simulate this first one that we're about to do? Hey, what if I take this magnifying glass and I pan this around the room, right? And I'm looking at you guys and you guys are looking at me, right? I bet that's going to tell us what the outcome is going to be for this first one, right? So let me do that, right? So, ooh, right. Guys, what do I look like compared to you?
Oh.
Upside down? Yeah, that's what I'm looking for. Upside down, right? I look upside down compared to you, right? You guys look upside down compared to me, right? In fact, I think it look kind of wobbly too. Like, I wonder if that's going to come out to be like a real image or something, because something kind of funny about that, right? But yeah, definitely upside down, right? So we're definitely inverted, right? It's more technical term, right? Let's see if we get that out of this one. Now, refractive lenses are going to follow a little bit different rules than the reflection, right? Once we got the rules established and the framework to solve all these. So let's just follow a couple rays of light. I'm going to follow one ray of light that's parallel to the floor across the top of his head. Right? So it's going to start us out. Okay, that's kind of similar to something we did the other day. Okay, but now what? Now what happens to this light ray? Okay? Well, the fact that we have a converging lens. Right? I might write that too after I finish this. Right? Converging lens. Right? It's going to cause this ray to converge. Now, where is it going to converge? Right? It's going to converge through this focal point right there. That's the point of that focal point. Right? Now, that's one ray of light. What if I had like 10 rays of light all parallel coming from the left? Do you think they would all go right through that focal point? Yep, that's what a converging lens will do. I should label that. I'll call it converging lens. Right? Converging lens. I guess all three of those are converging lens, right? I'm going to label this last one magnifying glass. Magnifying glass. Because I bet dollars to donuts, it's going to give us an image that's the object blown up bigger. We'll eventually get to that. Okay, so back to here though. All right, so that's one ray of light. Now another rule for lenses, you guys good so far? You guys up to it? Okay. Is that if there's a ray of light, let's go back to the top of his head, that passes pretty much through the center of the lens, it's going to go pretty much in a straight line. Right? Now, technically, with all these, including what we just did, there's two refractions, right, from the air to the glass and the glass back to the air, right? But we're going to sort of simplify this and say that this particular line I'm drawing right now pretty well goes like straight line through the center of the lens. Okay, right? Yeah, a little bit of refraction there, a little bit of refraction there, but basically a straight line. And oh, look where those two rays cross, right? Obviously the top of his head where we started this whole thing, but also over, hey, look at that. Isn't that an inverted image? Inverted image right there. Here's your inverted image, right? That's exactly what we saw when I was panning this around the room, right? Because you to me or me compared to you, we'd be like outside the focal distance because we're like so far away compared to each other. Yeah, we looked upside down compared to each other. Right? Not sure. That's what we just saw. Right. What if you have like some object on a focal point? What would that mean, right? Or have you guys ever? Let's do the ray diagram. See how this plays out. We'll see what. Right? So let's do the exact same rules, but as we just did, but maybe we'll get a little bit different outcome. Let's have a ray of light going parallel to the ground across the top of his head. Right? That's going to refract a little bit, refract right, straight through this focal point. Zip. Right there. Good so far. Kind of what we just before. Right. And then let's go back, top of his head. Let's go through the center of the lens. First, that'll just be a straight line. And ooh, look at that. those lines are parallel lines. How could I interpret that? Okay. I think this could possibly be like a projection, like if you want to like project an image, say like on a screen in the distance. I think that's related to that. That's what that could be. Right? Or what if you turn this around? Right? What if you have you guys ever maybe taken a magnifying glass and like tried to start a fire with it? Right? And let's say there's a leaf on the ground. And say I want to set that leaf on fire. So you like move the magnifying glass, but you got to move it in one specific point where that leaf would align with the focal point. That could like here's your leaf here. Here's the sunlight coming from right to left. All these parallel light rays from the sun, and it all gets focused on one point. Let's set someone on fire, right? Or you know what? I think a story you could pair with that too is telescopes. I got a telescope poster over there, right? So if you take two of these converging lenses, that's one way you can make a telescope, like the old, like hundreds of years ago, it's the first type they made, right? And if you align their focal points, right? Okay, so you got these light coming in like from a far distance, right? And you could focus on it and then magnify it that way. So part of that story. Right. What if you have the object inside the focal distance? Okay, now this one I'm already going to call, this is going to be our magnifying glass application, because you can see that right here, right? Magnifying glass application. Okay. So let's just follow those rules and see if that's what we get. So one line parallel to the ground, across the top of his head. Okay. That's going to refract through this focal point way out here. Okay, so it doesn't even refract very much, right? Because I guess this is getting pretty relatively flat by this point. And then, okay, now I want to extrapolate here though. Because here could be an observer. I'm going to draw an eyeball to represent an observer. Here's an observer right here, right, looking towards the left. Right. Right. What does that observer see? Well, this observer says it looks like this ray, you know, the way the brain would interpret it, came from this direction. So I'm going to dash off a line. Right, that's what your brain would interpret. See a ray light come this way. It's okay. Well, it looks like it came from like back there. Right, even though the light actually came from back there, but that's what it would look like to that observer. All right, and then the other ray light that we've been doing is let's go from the top of his head through the center of that refractive lens. Next, be a straight shot like that. Zoop. Much. Okay. Now, where did those rays cross? Ooh, they cross back here. And look at that. We got a blown up image. That is exactly a magnifying glass, isn't that? Yeah. Yeah. Right. All right, you guys good with those? All right. You guys ready for diary? Oh, okay. Almost. Some of you guys have mentioned that. Okay. So we're about to flip the paper over and do diverging lenses and see what's the outcome of those. Diverging lenses we're about to do. So let's set up 3 dash lines, 3 dash horizontal lines. This is what we've been doing. We've got these baselines. Right, you guys getting 3 baselines. But now let's do diverging lenses. So, it's going to look something like this. Right, first thick on the outside and thin on the inside. Remember, this could be if you're wearing eyeglasses and you're nearsighted, which is statistically a lot more likely. Okay? I bet your lenses are also thick on the outside and thin on the inside. Something like that. Right? I'm going to call this diverging lens. Okay. Also, same as before, I got to sort of define how curved are these. So you do that with focal points. Try about what I did before. Let's go 2.5 centimeters, 2.5 centimeters. Let's go 5 centimeters and 5 centimeters. All right. And then what would it look like? 10 centimeters and 10 centimeters. I like that. Focal points. F for focal point. Let's get some objects on the board here. So let's go objects. Oh, wait, what am I doing? Pinking. Oops. It's silly. Right. I was going to try to save that for my images. Okay. So blue ink, I got object, object, object. I'll label that object, object, object. Right. Okay. Now, where's the image going to show up for each of these? Okay. And let's say maybe there's like an observer over here. Draw an eyeball, observer. Like that. That's good so far. All right. So diverging lens means if there's a bunch of rays of like parallel rays of light, it's going to hit this diverging lens, it's going to refract, it's going to spread out, hence diverge. Right. So let's follow a couple of rays of light, see if we can put the whole story together. Okay. So start one ray of light parallel to the top of parallel to the ground across the top of his head. Zip. Right. Okay. Now let's get hit this diverging lens and again, technically refract a couple of times. Guys, this is going to spread out like this, right? Like spread out, right? Right. In such a way that it would align with this focal point, right? It's a really tightly curved diverging lens. It refracts a lot. Right? Or another way to interpret it is maybe the object is proportionally far out. It's going to go like that. Right? So I extrapolated backwards through the focal point. Right? And if you have an observer on this side looking this way, right, sees a light ray emerging this, like diverging out this way, this brain would interpret it looks like it came from that direction, right? Okay, it's good so far. Right. And then also what we'll do, what we did for also the converging lenses is we'll do a straight shot from the top of his head through the center of the lens, right? Because there's a ray of light that will pretty well go in a straight line. Again, a little refraction, but pretty much emerge in a straight line. Okay. And look where those rays cross, right there. So there is your image. There we got object image right there. All right, we good? All right, let's try it for what if this guy's sitting right on top of the focal point? What's that going to do? So same rules we've been doing. Let's go line parallel to the ground, across the top of his head. Right, that's going to diverge, and then go ahead and line your ruler with that focal point to see exactly which way does that line, that light ray take off. Right, and then okay, so if you're an observer on the right side looking towards the left, you say, well, it looks like it came from. I'm extrapolating back straight through that focal point. Yeah, that's what it sounds like. What if this guy is, oh, whoops, and then let's go from top of his head through the center of the diverging lens, zip, and look where those lines cross. There's your image. Looks pretty similar to the first one. It's not really that different. That's interesting because the converging lenses that we just did got 3 pretty different outcomes depending on where was the object compared to the focal point, right? But those first 2 look pretty much the same. What if this guy's standing inside that focal distance? What's that going to do? Okay. So same rules. Let's go across the top of his head, parallel to the ground. Zip. That's going to diverge. But ooh, it looks like not as much in this case. Right. Yeah, and the other interpretation is maybe this is kind of a flatter lens. It's not curve so much. Think of it that way. Right? So extrapolate backwards the focal point. Okay. Let's go from the top of his head, straight shot through the center of that lens. Zip. Okay. And where those rays are crossing is right here. Image. Actually, all three of those like kind of sort of the same. So maybe it doesn't really matter where the object is standing compared to the focal point. You get kind of the same outcome regardless, right? Right. And that's why on my poster version, you see that over there on the wall, or if you're watching the video, you can go back a few days ago. I went through all the posters. Right? I only give you guys one example of a diverging lens on the poster because it's kind of only one outcome. But we did three because I want you guys to for sure see that that's going to be the case. All right, guys, good with those? All right. All right. You guys, club photo schedule. You guys got that all straight? Anybody have to go to clubs at any point like that? Okay. All right. So yeah, we have a few minutes left. What I'm gonna do is, just before you walk out of class today, just throw your ray diagrams in the grade tray. Get that checked off. Should be easy points in the grade book. All right. So last 2 minutes we got. I want to look at in these posters. There are 4 photographs included that were taken by telescopes, right? And each of these has an interesting story behind it. Right? So here's a black hole image taken a few years back. Einstein ratio gravitational lensing. I'll talk about this when we get to relativity and dark matter. Hold on to that idea. That's kind of that. Right? Hubble deep field. I think I told you guys the story the first couple of days of school, if I remember right. Right. But this one right here, microwave background radiation. So remember that this whole electromagnetic spectrum, there's only a tiny, tiny, tiny portion that's actually visible to our human eyes, right? But what if you could sort of see these other parts of the spectrum? And some animals can see a little bit here, a little bit here from the UV or the infrared, right? That could be helpful, especially for astronomy, because like as the universe expands, almost everything gets relatively red shifted. So some things that might have been visible, maybe would have been red, get shifted to the point that they become infrared and we can't see them anymore, right? Or a bit just even in general, aside from visible, right? That there could be information that's just generally spread out, or information that you could get that's generally in this part of the spectrum, right? And we do have telescopes that can see into the infrared, microwave, and there are even radio telescopes too, right? They're getting data from the universe that's like in this part of the spectrum, right? So you can take information, say from microwave, you can like crunch these waves and convert it back to visible, and that's what this image is right here. This is the cosmic microwave background radiation. And this can see all the way back, like the further away you look, because it takes time for that light to travel, you're also seeing back in time. This is as far back in time and space as we can possibly see. This is called like a baby picture of the universe when it was only 380,000 years old. And you literally cannot see anything back before this because the universe was too condensed for light to even, like any kind of light to even exist, right? Whatever EM waves there might have been, they just didn't travel anywhere, right? But starting from this point going forward, right? Right. So yeah, so this was taken in the microwave part of the spectrum and is converted to visible light, right? But what if we go the other way? What if you want to see something in the UV part of the spectrum? What does that look like? Because like some insects, some birds can see in the UV. So what does it look like in the UV part of the spectrum? Right. And I got the answer right here. Got Veritasium made a whole video on that, the UV camera. So there we go.